What's your job title?
Threat intelligence analyst.
And I'm a security response engineer.
Cool. So the layout of today, we're going to go through a talk for around about an hour or so. Then there's going to be a practical afterwards where you're going to reverse some binaries. Yeah? Yeah. Yep. All sound good? So I'll nothing to it.
Yeah. So my name's Alan. So I work at Symantec. I've been working there for about 5 years, and I've been working as a threat intelligence analyst. Initially, when I joined Symantec, I was a reverse engineer for about 3 years, and moved into a different team. So what I actually do in my current role is we investigate all high-profile attacks, and we track the attacker groups that are behind the attacks, and we present some of our findings in terms of papers or presentations or conferences. Do you want to give it a little bit yourself?
Yeah, so I'm a security response engineer. Basically, my day-to-day duties are that I take samples, just binary files of malware, and I analyze them. I work out what they do and how they do it, and sometimes why they're doing what they actually do. Then we tend to write definitions or just ways of detecting the pieces of malware, for Norton customers, and usually that comes in the way of looking for specific types of behaviors or maybe other key things that we can actually detect specific files on. And then, say, just like Alan, we also do some kind of deep analysis where we go into a little bit more detail for specific samples and families, and then we occasionally present these type of things at conferences, produce write-ups, papers, that sort of stuff as well.
Okay. So just for the agenda for what we're going to cover today. So going to start off with just playing a little video, Symantec video, so just kind of show them what type of stuff we do there. I'm going to use that as an introduction to why reverse engineering is actually important and why we need people to get into it, because the field is very small, there's very little people that do it. There's so much malware that we have to look at every day from all the customers that submit it to us, so it's actually quite important to get people interested in it. And it'd be really great if people could start doing it in colleges, so we wanted to come around and present something like this to us today for that reason. We're also going to talk about the P file format. So this is the standard binary file format that's used on Windows. So any of the things that we're going to talk about today are going to be geared towards the Intel chipset. So this is 32-bit architecture. I'm also going to talk about assembly language, so we're just going to do a crash course. So kind of basic revision, introduce you to some of the basic instructions that you can run on the Intel chipset, and what you'll kind of see when you kind of start reversing some of the malware as part of the workshop. We'll talk about the tools you'll be using as part of the workshop. So I'll just show you some screenshots, what they are, how they work. And then afterwards, Cathal will give you a demo. So we'll run down through one of the challenges, and we'll be able to basically go through the tools, show you how you open and run them, what you can expect to see. And then we'll give you a bit of verbal about what's expected from the challenges that you'll be working on as part of today. So video time. It's only about 3 minutes.
The cyber world is the wild, wild west.
Hackers use personal accounts to attack hundreds of new targets.
Every second, every minute of the day, people are using this type of attack.
It gives criminals new openings to steal personal data and intellectual property.
Cyber attackers are more sophisticated than ever, using advanced tools to get inside more networks, faster than most businesses can defend against. Advanced attackers targeted 5 out of 6 large companies in 2014, a startling 40% increase from the year before, and they're more deceptive than ever. In 2014, we saw them hijack companies and use their own networks against them. Once inside the breached network, they leveraged existing IT management tools to move stolen IP around. Others created custom attack software that they deployed from their victims' own servers. And many used stolen email accounts to spearfish the next victim. In 2014, there were 24 critical or zero-day vulnerabilities discovered. We saw cyber attackers exploit these holes much faster than vendors could create and roll out patches. The top 5 zero days left companies without a patch for 295 days. From data centers to desktops, companies of all sizes are seeing an increase in cyber attacks. Nearly 1 million new pieces of malware are released every single day. In 2014, 28% of it used various tricks to avoid detection in virtual machine environments. None of us are immune. In 2014, we saw a 70% increase in scams shared by our own friends on social media. Roughly 1 in 6 Android apps turned out to be malware in disguise. On top of that, digital extortion is also on the rise. 45 times more people had their devices held hostage in 2014. Together, let's make 2015 a better year for digital security. Download Symantec's 2015 Internet Security.
Yeah, I'll stop it there. So basically that was just a kind of introduction to show you the amount of malware that we actually get in. So we're getting like tens of thousands of pieces of malware get submitted to us on a daily basis. We have to get reverse engineers to be able to reverse engineer them, find out what they do, how they're doing it, if they're actually malicious. And we can use that information to then protect customers by writing definitions and detections that we can push out either through our AV engine or through our IPS engines. Also, reverse engineering is not just focused on malware, it also can be applied to other aspects of security. So you can use this for like vulnerability development. So for example, if you're doing vulnerability research, it can be used for writing exploits, it can be used for identifying bugs in software. It can also be used to identify or even understand proprietary type formats. So formats for file types that aren't actually made available or they're closed source. And it's the same with software, anything that's closed source, you can use reverse engineering to gain a better insight to how it works and what it's actually doing on the system itself. So we'll start by just talking a bit some of the concepts behind some of the things you'll see today. So one of the most important things is the P file format. So this is what the structure of any file is used, or it's actually stored in on a saved to disk. So any executable file you'll come across. So I'll start with just a basic example. So in this example, I just wrote a simple hello world, and I was able to compile it on a 32-bit system, and I was using Visual Studio 2015 for this. When it gets stored on or written to disk, it'll look like this when you open it in the file viewer. So you'll see the ASCII on the right-hand side, then you'll have your hexadecimal codes, and then you'll have offsets on the leftmost column. When you decompile this using some of the tools, such as IDA, which we'll be using today, you see that it gives you assembly representation. So that's the push, move, push, call, etc. instructions that you'll see. On the left-hand side of that is actually the opcode instructions. So this is just one level above machine code, which is actually executed on the architecture or the chipset itself. And when you run the sample, it takes that machine code and it gives you the expected output from your program. So when you write any disk or create any file from source code, it'll get written to disk, and you can open up a file viewer and it'll look something like this. Code translated into opcodes. Opcodes are represented by bytes, which are hexadecimal bytes. The highlighted code here that you can see, so the bytes, there's only about 20 bytes there that are actually highlighted. That's representation of the C code that you wrote. So that's the only bit of code that's actually in the file that was generated from Visual Studios. So the question then brings up, what is all the rest of the stuff that you're seeing when you open the executable files? So this is what P format is. So this is, by understanding what the P format is, you're able to understand the concept behind the file, how it's structured, and to be able to pick the most important parts that you'll need to look at for reverse engineering. So this is the standard or basic layout of any file that's stored on your disk. So you have your multiple different regions that are part of the file itself. So for example, you'll have like a DOS header, you'll have a P header, optional headers, section tables, etc. The P format was actually introduced as part of Windows NT. It was actually created by a guy called Mark Zawinski, if I'm pronouncing that correctly. And you'll actually see when you open up some of the files, you'll have an MZ at the very top, and that's the very first offset. So he used his own initials as part of this when he was creating this format. There's some, if you were to download the Windows SDK, you can actually have a look at some of the header files, and there's one header file in particular, winnt.h, and it will give you the whole structure of a P file, what are basically variable by variable. So you'll be able to identify the sizes of different variables that are actually discussed. So this is one of the structures, so the first header, so the DOS header. So again, as you mentioned, the first letters that you'll always see when you open up any executable file are NZ, so that's representation of the guy who created it in the first place. This is actually known as a magic number or file signature. So when you open any other files, like if you were to open a zip or a Java file, you'll actually see that they have their own file signatures. It's usually at the first offset of the file. Java was kind of a funny one, where the creators of Java and Jar stuff They were actually sitting in a cafe and they were discussing how they were going to create this file format for Java to run on their JVMs. And they were noticing the waitress that was there in the place, and they decided to call it Cafe Babe. So there's other similar ones as well when you actually look through all the different file types that you can see. The whole reason for the MS-DOS header is actually just to ensure backwards compatibility. So for example, if you were to execute a P file on a machine that doesn't support it, it will just print this file cannot be executed. You can see that same string in loads of samples. So it's going to be an MP file that you come across. As part of the DOS header, there's certain offsets, which actually refer to the next sections. So this is true for any of the headers that we come across. Any offset will point to the next section, so it's all in a sequential sequence. It's all basically stacked upon each other, so it's all very linear. The P header, so this is known as the full header, or the file header. This basically gives you some information about the file and how it was constructed in the first place. So it will contain information like the architecture that the file was compiled on. It will also contain the number of sections that are in the file. So sections might handle or store the code that you write, such as like the hello world. It'll also copy strings into certain sections of the data section. It'll also give you some additional information like when the file was created. So you have our timestamp data there. You'll also get the size of the optional header, which is the next section that follows. And you'll also get some characteristics of how the file is supposed to execute on the machine. So is it a DLL, is it an executable, so what's the machine going to do with it? And the optional header is the next section. So despite its name, it's not optional, it's actually required to be as part of the P file structure. Comes directly after the P header, and it contains some additional information again. So you'll be able to get a lot of information here in terms of the version of info compiler again, the actual size of the file when it's stored on the disk. You'll also have checksum values, so we'll be able to ensure the integrity of the file. And there's loads listed there. You'll notice from the struct on the left hand side, and you'll see like short, long. This is to denote the amount of bytes that it's actually going to take up. So when you jump to example for the optional header using a hex header, you can actually determine which field you're looking at based on the number of bytes that are being used. One of the most important fields is the entry point. So this is where, when you execute any code, the entry point is selected, and the first bit of code that actually runs, or the first instructions that it runs, are always pointed to like the entry point. So this is usually the best point to start, because it's going to be the beginning of your program, of your code that's executed. There's also some additional sections. So sections are actually used to store different types of data. So for example, you have a text section. Generally your code that you write in like Visual Studios or whatever, it's going to be stored in that section. If you have any strings that's part of your code, they're going to be stored in like a data section. So you'll see like in some formats you'll see like string tables, etc. And you'll also have like a resource section. So this is a section where like icons for the application itself are stored in PNG format, etc. So there's loads of modules out there as well. And you don't need to have a complete full understanding to be able to start reverse engineering. It's just to be aware that it's there and it's a concept. So when you open up a file in something like IDA, so a compiler or a disassembler, you'll be able to see that there's loads of information there, but there's only a subset of that information that's actually may be important to you to complete the task at hand. There's P module, and that's actually ready for Python, which allows you to start parsing these yourself, and you can pull out certain fields. You don't really need to use that part today, but it's something that you can actually go ahead and start playing with and experiment with to kind of get more familiar with the P structure. It'll even give you the ability to overwrite some of the information in the fields. And if you're able to change the values, you can see how the system actually reacts to those value changes. So if you were to manual some of the values, it might operate in a different way that's unexpected. So that's just a code snippet of like accessing the P timestamp, for example, using the Python module. It's quite straightforward, it's quite easy. It's something that's used in a lot of applications, especially by reverse engineers for writing quick scripts to be able to pull information they need from files, or even decrypting strings that might be embedded within them. So an assembly crash course. So everyone runs usually 1,000 miles the minute they see assembly or hear about assembly, they don't want to know about it. It actually has a stereotype of being quite complicated, but actually once you get into it, it's not any more difficult than any other language. It's just getting the basic concepts down, and once you have those concepts and know how it actually interacts with the system, with the chipset you're working on, it's quite straightforward. And you can kind of cut through all the crap and just get down to stuff that's actually important to what you're actually trying to figure out. So what is assembly language? So generally you start with higher level languages like C or C++ or Java, etc. When you compile them and link them, they'll actually be converted into assembly language, and there's generally like a one-to-one mapping between opcodes, which are instructions, that are represented by assembly language. So in most cases there is, in some cases there isn't, but you'll see that as you start going through a bit more of assembly. That in turn gets generated into machine code, which is then executed on the chipset itself. So the chipset will have a number of instructions that it knows how to run, so once it gets these instructions it will do certain things to be able to interact with the program that you're writing and to the system itself. Some of the basics, so registers, obviously fundamental. I don't know, is there many people here who've ever done assembly before, or I don't know if they still do the D6. Do they do the D6 here still as part of CA?
They do MIPS.
Yeah, MIPS. Okay. So yeah, so the concept of registers might be new to everyone, but they're fundamental in how you actually understand and how you store data and things. So you're generally given a number of registers that you can play with as part of your assembly code. You have general purpose registers, so you have EAX, EBX, ECX, EBX, ESI, EDI. E is actually denoted for extended, so when you were back using 16-bit architecture, it was just AX, BX. So they extended it to 32 bits, so they added E. You'll even see on 64-bit systems they're referred to like ORBX, ORAX, etc. ESI, so this is the source index, so this is usually where you get offsets and strings and things. And same for EDI is the destination index. Two of the pointers that are going to be very important are the stack pointer. So this is where it's pointing to information that you're storing as part of your program itself. And EBP is the base pointer. So this is going to be pointing to local variables as part of functions or code that you're writing. They're actually split into different levels. So you have higher levels and lower levels, like AH, AL, BH, etc. They're split into 8-bit parts. And total 16 bits, and then total of the whole register is 32 bits, hence 32-bit architecture. So the stack as well. So just want to give you a basic introduction of what the stack is, because you'll see a lot of code when you open it up in like some of the disassemblers that will start referencing ESP and EBP, so you need to know what that actually is. So the stack is basically part of the memory where it stores variables and function arguments. It works on the premise of last in, first out, so LIFO. So if you want to add something to the stack, you push it using the push instruction, so it adds it to the very top. And when you want to remove something after it, you just use pop and it just takes it off. So if you were to push 3 or 4 things onto it, it only comes off in the order you put it on. So you need to keep that in mind when you're pushing stuff or storing information that you might try to remove later for use. It actually goes backwards. It goes from the highest memory location down to the lowest. And you use ESP and EBP to be able to reference some of the data that you're storing on the stack. So for example, ESP will point to the top of the stack. It'll keep any of the arguments and stuff that you have or some of the functions. And EBP will point to some of the local variables that you're declaring within the function after a call. So for example here, so you're declaring, for example in C, you have 3 integers. We're pushing 10, 5, and 2, quite simple. When you convert that into assembly, you'll just see like push 10, 5, and 2, and then there's a call to a function. So one of the concepts that you need to kind of understand is how the stack operates when you enter functions. The system itself needs to be able to keep track of when you enter a function and when you come out of a function to be able to continue execution after that point. When you push them onto the stack, they actually get pushed in the order that they're pushed on. So you'll see here you have A, B, C represented by ESP-A plus ACE plus 12 plus 16. Can anyone tell me why, actually for example, can anyone tell me why it's giving a reference of like ESP plus ACE for A variable?
This addresses are 4 bytes each.
Exactly, yeah. So integers are 4 bytes. So it's going to be pushing it on in 4 byte blocks. So if you want to reference one of those variables, you need to be able to make certain change and offsets from the stack pointer to be able to access them. Once it enters the function, it'll save the base pointer so it knows where to return execution to. And then it'll create a new 4 byte integer called result, and you'll be able to store the result in that, and then you'll be able to access that using negative values. So there's a piece of assembly code you'll always see. This is part of when you enter a function. So this is called a prologue. So this is when it saves the base pointer address that it can use to return at a later point to continue execution. X is actually the amount of the size of the amount of bytes of the variables that are used in the function. So any variables that you declare within it. In C, it looks something like this after you call your function. And when it's represented in assembly, you'll have push EP, and it's using 12. So again, integers are 4 bytes, because there's 3 bytes, you'll be using 4A12. So that's where you're getting, it's making room on the stack to store that information. They can be referenced using -8, for example, if you wanted to access one of the variables. I'm just going to go through some basic instructions. So this is going to be just simple assembly stuff. So there's a structure there, or notation that you need to understand how it operates. So destination always becomes the source. So if you want to move, for example, a certain digit or hexadecimal digit into a register, you denote it by the source into destination. So there's a couple of examples that I have here. So if you wanted to move, for example, 3 into EAX, this is the assembly code that you run. But this is just basic data movement around, how you move stuff into registers and things. EAX register will look something like this after that operation is run. Can anyone tell me what the difference is when you use square brackets with a register? Exactly, yeah. So it's referencing the contents of a memory address. So if you see in like C code, for example, you have pointers. You'll have a memory address which might point to a piece of string that's stored somewhere in memory, and then you can access that string using the square brackets. So that's the contents of like a memory address that you're going to be pushing in, or moving into the EAX register that you can start using then. So that's for example, if you were using a string that 4010000, if it was pointing to a string called hello, that's what the EAX would look afterwards. So push 10, so if you want to push arguments, so let's say for example you have arguments as part of functions, you'll push them before the function is called. So for example, you can just push variables, so in this case 10. And you can also push offsets to strings. So if you have again like the hello world, when you disassemble it in something like IDA, you'll get code that represents stuff like this, where it's actually pushing a string onto the stack, where it may be calling printf, for example. So the offsets will basically give you an idea of where those strings are stored in the file. Again, if you want to remove them from the stack after you push them on, you can push something onto it, you can run whatever additional instructions you want to run, and then you can just pop it off, you can pop. And again, you don't always have to just push variables themselves. You can actually use registers to push stuff onto the stack, and that's generally how compilers will actually use it. They'll move it into a register, and then they'll push the register onto the stack. And you'll see that a lot as well as part of the work. There's also load effective address. So for example, when you come down to looking at some API calls, you'll see that it actually loads basically a memory reference into one of the registers, and to do that it actually uses load effective address instruction. So it will take a pointer to that, and it'll be able to call it directly by calling the register itself. So in this case it was calling it on EBX. And there's loads of other instructions as well. So these are some of the arithmetic and logic instructions. So again, if you're wanting to add values together, you can move something into a register, and you can just use the add instruction to basically add them together, and then the result will end up in EAX. And there's it's important to note that some of the instructions that you actually do will have effects on other registers. So for example, if you divide 65 by 4 in this case, you'll get the results stored in a certain register. But can anyone tell me where the remainder ends up?
EDX.
EDX, exactly, yeah. So when you're actually executing some of these instructions on the chipset itself, it'll affect other registers. So when you're using one of the debuggers, like Ollie debug, you'll see as you start executing some of the code or stepping over it, that other registers will start to change, and they're a result of some of the instructions that are run. So keep that in mind when you're going through things. Some of the registers will change, but they'll be highlighted in color representation. And then there's control flow stuff. So for example, if you were to call into a function and then you expect a result, so in this case it's going to be like an integer result, 0 denotes success. In most cases where you have -1 would be a fail. You can use CMP to compare the results that's stored in the EAX register, and then you can jump, if not 0, over to a fail block, or you continue execution. So it's quite simple to do if blocks, and that's an example of what something might do when it succeeds or fails. And there's loads of other instructions as well. So you have like jump if equals, jump if not equals, jump if 0, jump if greater than or equals, etc., etc. And you also have your call and return subroutine call as well. So in this example, we're moving a value into a certain register. In this case it's EAX. We're pushing that onto the stack because it's going to be used as an argument to the function itself. And then you'll see that it calls the function. So that's noted in red here. So this is an increment function. Then we compare what happens to the result afterwards to see was there an error that occurred. So if you're always going to be passing something that's greater than 0, you expect the answer or the result to always be greater than 0. So we can check that against that here. So let's say, for example, within the function itself, again, as we had a quick introduction to it, you'll see you push EBP, so it's saving the stack so it knows where to return execution to. So you'll see that all the time. So it's something you don't really have to pay so much attention to when you're looking at some of the disassembly code. Then you'll see add EX1, so this is adding 1 to the number that you pushed into the function. And then it's returning or restoring EBP so it knows where to return execution to. So the only important thing in that whole function is your add to the function. The rest of it's only being created by the compiler to be able to keep track of where it's actually executing in. Then it will do a return, and the value is stored in the EX register, which then you can use your additional instructions to be able to operate on that register itself or whatever conditions you want to check. There's lots more, obviously, of these opcodes that are there. There's only so much time that you can actually go through all of them. So this is one of the maps that's actually really useful to any reverse engineer when they're starting out. Essentially, you'll have every single instruction that's available to the Intel chipset. So this is any 80, 86 or 32-bit architecture. To be able to use the map, for example, if you were using a push, that's instruction 68. So you can go along on the left-hand side, you start at 6, go across to 8, you'll see that's a push. So some of the what's kind of interesting as well, some of the instructions, you see like if you do like a D0, they're actually not documented by Intel at all. But if you actually were to overwrite some of the instructions within samples and you execute them on the chipset, you'll see they actually do things. In a lot of cases they don't document them, we don't really know why. But if you were to compare it against other architectures like AMD, you'll actually see those instructions are documented so you can get a feel for what some things do. There's a lot of experimentation you can do as well, which is kind of interesting. You can kind of see how the chipset works and does things with some of the undocumented instructions. If anything's going to be used by a compiler, generally any of the instructions that you'll come across will always be documented, and there's always something you can reference, or just do a quick search on Google to find out what they do. So play around with it is the best way to learn, really. So when I started, after I finished, I did a master's here in DCU after I did CA, and I went directly into Symantec after I graduated, and I joined the security operations team as a reverse engineer. So they do like a minimum of 3 months assembly language teaching, and they train you up before they get you to start looking at some of the malware to see how you kind of get on. The best way to do is just play around with different things. It's not something that you can kind of sit down a couple of hours and just kind of learn. You need to kind of feel for how instructions are executed, how files are structured. And the best way to do it is just write programs, decompile them, have a look at the code, what it's generating, write simple functions. So, and you can easily do that on any architecture as well. So for example, like even on Linux or on Red, you can compile a simple program like Hello World. You can use GDB to run the program and use this main to basically disassemble the main function and have a look at the code that you're being generated. Again, it's the same approach for any of the other architectures. So there's other file formats there, like ELF, which is on Linux, and again, Mako, Java, etc. And one of actually really good, which I found personally when I started learning, was developing on what I used to use all the time at home was FreeBSD. So this is part of the Berkeley BSD 4.4 subsystem. There's a website there called int80h, which is an excellent tutorial. It gives you a whole tutorial on NASM programming for Unix systems in assembly. I highly recommend checking it out. It'll give you loads of information, and it'll give you loads of tidbits and a bit of information about different things that you can do as part of reverse engineering, and even starting to write some assembly language programs. So that's an example there of simple hello world. Run it in GDB, decompile it. You'll see again, you have your, this is on the 64-bit architecture obviously. So you'll see different reference names for RDX and EDX. So it has like RVP, RSP, exact same. This is the prologue, so it's storing that information to be able to know where it returns to for execution. Basically moves EDI, which is a reference to where the string is stored, and it'll call it. So it's important to know as well on some of these architectures, Intel uses the source followed by destination, AT&T syntax reversed. So this is why you're seeing the string or the memory range there being referenced first, which is being moved into EDI and not the other way around in Intel. For any of the ones you'll be doing today, it'll all be the Intel, just FYI. So some of the tools that you'll have as part of the workshop. Q, so Q is basically a hex viewer. It's been designed especially with the purpose of being able to parse the P file structure, so it can give you a lot of information about the file itself. It's very useful to use to triage the samples. Again, you can see NZ in the top corner for P file. It looks quite ugly, but it's actually very powerful and very fast, and it's something that we use ourselves in Symantec every day. There's different types of views and access that it can give you to the file itself. So obviously you get your ASCII representation on the right-hand side, your hexadecimal and your file offsets. It'll also give you access to certain sections, so like the text section where your code may be stored, or data section, resource, etc. We have legends as part of this that will give out, or not give out, but it'll be in the VM yourself that you downloaded. So it'll give you a kind of reference of all the keys that you can use in the shortcuts to be able to access certain parts of it. And again, they're all available online, so you can quickly Google for it. It'll also be able to disassemble some of the code for you as well. You can do it in 16-bit and in 32-bit. So it'll give you basically the assembly for any of the codes that you're coming across. So it'll interpret some of the opcodes, give you the assembly, and you can use that quickly to look at some functions or jump into functions to kind of get an idea of what to do. And you'll also be using Ollie debug. So this is a debugger. So this is a program where you can run or open your code or open your program with, and it'll give you a disassembler, it'll give you all the assembly and the instructions, and it's able to highlight certain calls and functions in certain colors to kind of give you an idea of what's going on. It'll also be able to show you certain conditions like jumps, be able to highlight them with arrows. You'll obviously get your stack on the right hand side, you'll get some of the flags, you'll get here's your stack here, registers on the top, and you'll get a memory view at the bottom there, and you can actually step and run through some of the instructions, right? Pressing F7, for example, to step into or step over. So you can run them, you can see how it affects some of the registers, see what happens when it goes into memory, etc., etc. This is the assembly part, so the assembly window, and what you'll expect to see. You have your registers view, it's on the right hand side. So again, you have your EX, ECX, EPX, etc. There's also some additional flags. EIP is actually very important. So this is the instruction pointer. So the instruction pointer is pointing to the current instruction that is going to execute next. Any of these fields, you can use Ollie debug to modify them. So if you want to change the contents of an EDX register or the result of a function, you can literally jump in, just double click them and modify the value so you can see how it reacts in certain ways. So for example, if you were opening a program and let's say it's checking for a certain condition like a license file, you might see that they only have a function to check for a license, and then if you were to just modify a quick jump saying yes, success, got license, change EDX to 1, you can just skip all the whole license checks in one program. So you'll also get your stack view, so this is when you're pushing in public stuff like the stack. So you'll see in this case it's giving memory references, so anything like 7s and 9s kind of one of the ranges you'll see for DLL files that's loading in. We'll also see references to strings or stuff that's stored in memory as part of the program once it gets executed. And you'll also get a memory view, so you can have a look at the memory itself and get different representations. So it'll let you have a hex view, you can change it all to strings, you can change it all to different types of interpretations. That makes it easy for you to analyze it a little bit better. So these are some of the shortcuts. There's lots of them to do things. I think Cathal included this deck in the VM already.
I did not.
Okay. Well, I'll put it up on my Redbrick account, and if you can download the deck so you can use it as a reference point anyway. All of these shortcuts obviously are, if you have a quick Google, you'll find them as well. And there's IDA, which is one of the other tools you'll be using today. So IDA is a disassembler. It allows you to do static analysis. So basically, it just gives you the assembly representation of any file that you open. It also allows you to do some debugging. In most cases, personally, I find IDA is easier to debug with, and I use IDA for static analysis. So you can basically go down, jump into functions, see what's actually happening, and see any calls that it makes or references to strings or where it's going to be stored in the file. There's obviously a lot of information available that's part of IDA. It's a very complex system to use. There's whole books devoted to it, which are like that big. Brilliant book. When we came into Symantec, the first thing they threw at me was this. They were like, best of luck, see you in 3 months. So I highly recommend check it out if you can. There's lots of really good information in there. So you have different types of views as well as part of IDA. So you'll get some of the assembly stuff in a flat view. It'll also give you like graphs, so it'll show you the functions that you're going to. There's some of the shortcuts here for IDA itself that you can have a look through. So it'll give you some of the navigation stuff, so how to jump around or cross-reference offsets and things like that. Navigation view, which is detailed by the top, with different colors indicate different parts of the file. So it'll give you basically different ideas of what's there and how much data is stored in different sections of different types of data. And you'll also get like string view. So you can have a list of all the strings that are available in the file that you'll be able to pull out. You can scroll through it. And this is actually a quite good way to start. So you can basically pull out the strings and anything interesting that you see, and you can just double click it and it will bring you to that function where that string is referenced. You'll also get a list of all the functions. So as part of IDA, for example, if you start analyzing something and you find a function that does a certain thing, you can actually name the function, which makes it easier, and it'll name that function anywhere that you see it. So for example, if you had a printf or something like that, which you wrote yourself, you can name it printf or myprintf, and anytime that's called within the assembly, it'll have that function name, so you know exactly what it does already, so you know you don't have to reanalyze it again. And Cathal is going to give you some information on the challenges. I know there's a lot of information here, and probably a lot to take in very quickly. Don't get disillusioned by it, and don't get kind of put off by it. We'll be here for the whole day, or for most of the evening anyway, to give you a hand as you work through the challenges. And it's something that's very beneficial for you. I think it's going to be good if you want to get into reverse engineering, just to get a basic understanding of how things work. Obviously, there could be potential for follow-up ones where you go into a bit more detail, but we just wanted to cover some of the basics and some of the basic tools that you may use as part of reverse engineering. I'll let you talk about the demos themselves and what's expected. I think you have a demo as well, do you?
Yeah, I do. So I'll just swap out the laptops instead. Okay, so for all of the different challenges, they're just simple C programs really that I wrote in Visual Studio, and I just kind of compile them and I disable all kinds of optimizations to try and keep them as clear as possible, because the way the compilers work is they try to obviously make things as fast or as and the binaries as small as possible, but what really happens then is that you end up with pretty much unreadable assembly language. So what we'll do is we'll kind of take one of the challenges, the more simple of them, unfortunately, and we'll just kind of go through it ourselves. So we'll say this then is an example then of just the type of code that we're actually talking about. So we'll say this is what the actual code would look like when I wrote it in C++, just normal everyday kind of C++ code. There's something really complicated going on in it. Then, as Alan was saying, once you kind of put it through the compile process and you link the executable, what you end up then with is the type of assembly language representation that Alan's been kind of going through. So like, just so that connection is at least clear in your minds, that you're basically going from source code to binary, and now you're going from binary back to not source code, but something which is at least understandable and something that you can begin with. So we'll say, if you end up on your system with some random executable, you don't know exactly what it actually does, then, you know, where would you begin? So then for the workshop, you should all have virtual machine downloaded already, I hope. There's a command prompt icon on your desktops, which you can double click and it will drop you into the workshop directories. And in Alan's talk, anything that would maybe jump out at you that you might try, any tools from even Linux or Unix that you might think would be useful in a situation like this. Remember, you're trying to find a password. You think the password is probably written into the executable somewhere. So, you know the password is an English string. Anything jump out at you?
Strings.
Strings, yeah. Okay, so that's probably a reasonable guess, right? So hopefully now the password. No, we don't. So we'll just jump straight into it then. On your desktops, I've put shortcuts to the three tools that Alan mentioned. There's a shortcut for Q32 demo, a shortcut for Ollie debug, and then a shortcut for IDEF free. Okay, so if everyone just wants to click into the Q32 shortcut, and we'll begin by having a very quick look at this first binary. Okay, so when it opens like this, you'll probably see it like, you know, it's basically giving you a listing of where Q is actually currently installed, and then we'll say the two dots at the top, just click those. You can navigate up and down these different directories just using your up and down keys. Go all the way up then to the two dots to jump up to the C root drive, and then go to the workshop folder, and then select reversing workshop 0.exe. And when you select it like that, you're going to get this strange looking blue screen. So again, Q is extremely powerful. It looks really simple, but it's very, very deceptive. It will parse an entire PE format for you pretty much instantly and let you kind of jump around and look at different parts of it. One thing definitely worth mentioning is that you can even use Hue to open your disk directly to, if you want to look at, we'll say, boot sectors or stuff like that. It's an extremely powerful tool and very well written. So if you hit return then, you'll move into the second of Hue's default views, where you kind of see these hex machine code, and then you've got the ASCII representation then on the right hand side. So as Alan was mentioning then, you see the NZ header right at the very top, and then if you kind of just page up and page down, you'll see actually that there's huge amounts of empty space, and then you get kind of into the machine code itself. Again, it all looks like gibberish. There's no kind of ASCII on the right hand side which will give you any idea about what any of this code actually does, okay? But Hue has a lot of kind of nice features which, full screen. So if you all press and hold Alt and then hit F6, so you should then see a kind of a string output just like this. So this is basically, you're asking Hue to pull out every single English string or ASCII string basically in the program and show it to you. And then you'll be able to kind of jump up and down and have a look straight away at what type of thing is actually in the program. So we'll say that would be another way that you might be able to start looking for a password in a program like this. You know, you basically pull out all of the strings, have a look if there's anything actually jump out at you. So you can see that, hopefully you can all see that there are actually a lot of English strings in this, and maybe again there's an awful lot of noise in there as well. A lot of stuff which is basically just added by compilers and libraries and that sort of stuff. So sometimes it's easy, sometimes it isn't. I mean, unless you know it's actually a password or something. So yeah. So again, Hue will basically parse through the entire PE for you, and you can kind of jump around. So we have the text section then at the very start. You can get to this view by pressing F8 and then F6.
F8.
Say again?
Alt F8.
Just F8 by itself. And then this will basically show you all of the sections in the file. So anyone have any good ideas where a password string might be stored, in which section? So we've got .text, which is generally used for code, and then .data and .ordata, which are usually used for, well, data. So anyone have any good ideas where you might start?
Data.
Yeah, the data section is probably a good idea, or maybe the ORData section, right? So again, like, it's a case where you're just kind of using what you're finding out about the PE format itself to make educated guesses about where useful parts of the program might actually live. You know what I mean? And again, I know it doesn't look right when you're kind of looking at executables in these weird looking blue screens, but it is very useful, and you can get an awful lot of use out of it if you keep at it. So if you just kind of scroll down then through your ORData section, you'll actually begin to see all of the strings that were output when we first executed the program. Okay, so this is where those strings are actually in the program itself. This is where they're ultimately read from when the program is executing. Okay, so you should then be able to see everything that we kind of printed out so far. So if you go back then to the section view, F8, F6, you see that we also have a kind of a resource section. So the way the binaries are laid out, the way they actually work is when you input the correct password, it validates that the password is correct, and then it will decrypt the final messages from the resource section. So again, the whole idea was that, you know, this is your prize for kind of working through these binaries and working out exactly what's going on, okay? So we'll say that's probably the lowest level of tool that we actually use in Symantec on a daily basis, but it's something that when you get used to it, you'll kind of go to it first. It'll be, you know, something that you would want to have bound to a key that you can immediately execute on pretty much everything you come across, because once you get used to it, once you get used to how you pull out strings from it, look at text sections almost straight away, it'll be almost always the first thing that you go to, because again, it parses the PE format for you, lets you jump around very quickly to specific things that you'll probably eventually want to see. So then, as Alan was saying, then the address of the entry point is usually one of the most important fields of the PE header itself, because that's basically where the program will begin executing and where you'll want to begin when you actually start looking at your own binaries in the field. I know probably this all seems a little bit complicated and kind of how does all of this kind of fit together, but it's kind of a real world example. Like, I mean, if you get used to using these tools, you can kind of go out yourself and basically start pulling apart almost any executable that you come across. So these are worth kind of sticking with. So we'll say if you press F8 and F5, you'll go to the very first instruction that is executed when the program is launched. And then if you hit return again, you get this nice assembly view of the code itself. Okay? So there are the three main views, and you get a few, and you get to them by just kind of hitting return to cycle through them. So you get your kind of weird ASCII view, your hex view with ASCII on the right hand side, and then finally your disassembly version of the code. Now I wouldn't really recommend that you go through the disassembly here, because it's very, very static, and it doesn't give you a particularly good idea of what's going on in the file, but it's definitely worth knowing about that it is actually there. Okay? So we didn't get too far with Hue, we just kind of saw a lot of blue screens. So the next thing then we can have a quick look at, if you open up Ollie Debug, and there's a shortcut on your desktops. And then if you go to File, Open, so this is kind of an assembly level debugger. Again, we're kind of talking about programs where we don't have the original source code. We're trying to find out what they actually do, how they work, you know, and what we can kind of find out about them just by looking at their assembly code directly. So again, it doesn't look particularly pretty, but the more time you spend looking at this, the better off you'll be. It's just kind of one of those things. So the highlighting works that Everything in turquoise then is just basically a call to a subroutine. Everything that's highlighted in yellow is a conditional or maybe unconditional jump. Hence, conditional jumps have black text. Conditional jumps have red text. Unconditional have black text. So again, this is how we'll say loops and maybe if statements in your programs would ultimately be represented in assembly. They use these type of low-level constructs to build up higher constructs, I suppose. Like these are the basic building blocks of your programs that you're writing in C or Java to an extent as well. Like everything that you kind of write in those high-level languages ultimately gets broken down to code that looks like this. So this code obviously looks extremely verbose compared to, we'll say, your typical C, C++, Java program. But at the end of the day, this is what it all kind of comes back to, this code that tends to look like this, okay? So then the last tool that we kind of want to have a look at, and hopefully you all have Reversing Workshop 0 open in Ollie, would be IDA Pro Free. Again, it's on your desktop, so just open it up, click OK, go work on your own, and then back to File, Open, and again navigate to C Workshop and open Reversing Workshop 0. Okay, so when everyone has that kind of open, can you go on? Okay, so if everyone, or if most everyone has kind of got to this point, you can just click OK. And then when it asks you to check the Microsoft symbol server, just say no. Okay, so we kind of get dumped to this kind of graph looking view here. So just hit spacebar and then you'll be back to good old assembly. Yay! Okay, so this is where IDA really comes into its own. It's why it's so famous. It's why kind of everyone who talks about malware, they'll say, "Oh, just use IDA. It makes everything so much more simple." Because IDA straight away, it basically tries to do very intelligent parsing of the assembly language that's actually there in the first place. Okay, so basically straight away at the top of the file, you can see that the procedure's name is main. It's main, right? So IDA immediately drops you in main. And then it basically tells you, okay, well, I have these two variables. These are variables that are actually defined inside of main, and then I have these arguments here. So do those argument names look familiar to any C programs, C++ programmers? Okay, they're kind of standard, we'll say, arguments that you might pass to the main function. Okay, so they should be maybe somewhat familiar. So this is just one of the ways that IDA tries to help you. It tries to immediately start giving human readable names to basically assembly language, which is by almost definition quite difficult to read. Okay, so that's one of the reasons why it kind of is so famous. It tries to help you out as much as possible to understand kind of assembly language gobbledygook. Okay then, so we'll kind of start having a quick look at what's actually kind of going on in this program, or at least in this part of the main function. So then you can see straight away at the top, the first few instructions are what Alan went through during his presentation. That's your kind of standard assembly prologue, okay? It doesn't look much better than we thought it was before, but okay, we still recognize it at least, right? And then we'll say if you jump down a little bit, you'll see that there's a call straight away to a subroutine, okay? So one of the nice things then about IDA is that it lets you immediately jump around inside of the assembly language so that you can check things out. You can say, okay, well, first things first, I see this subroutine is called almost immediately. I wonder what that subroutine actually does, okay? So if you can navigate down, just put your cursor on that subroutine and hit return, then you'll actually jump directly into the subroutine. So has everyone kind of followed us so far? Yeah, everyone gotten that far at least? And then we see, okay, again at the top, we have our typical procedure prologue, push EBP, move EBP, ESP. And then straight away, okay, we see we have a push offset, what looks to be a human readable string. It looks like something that we saw during the first execution of the program, right? And that's being pushed just before a call to another subroutine. So can anyone tell me what they think that string looking thing actually is? Like, how is that related to the program that's called just after, to the subroutine that's called just after? So I'm talking about this. Like, how are these two related? So one of did you ever hear that kind of expression that like C++ makes it harder to shoot yourself in the foot, but when you do it blows your leg off? Did you ever hear that expression?
No.
Okay.
Can you use that one now?
Well, the assembly version of that is, with assembly it's very difficult to shoot yourself in the foot because first of all you have to make a bullet, and then you have to make a gun, and then you have to make gunpowder. You see what I mean? So there's nothing that you kind of get for free with assembly. Everything that you see actually executing has to kind of come from somewhere. So you need all of these kind of low-level statements. You need basically strings pushed onto stacks before calls to procedures, which will eventually print your string. See what I mean? So we'll say code like this, where you're just kind of calling system.out.print with your nice parameters, and like, you're kind of spoiled in these high-level languages because you don't have to think about any of this crap. But when you actually, want to reverse engineer back from, we'll say, the endpoint back to the start, well then you're going to have to really begin to think about, okay, well how does this actually work on, we'll say, a processor or, we'll say, assembly language level? How is a string actually passed to a function? And then how does the function actually end up printing those characters directly to your screen? So in this case then, this string then is just basically the parameter that's being passed to this function here. So anyone have an idea then what this function might be? Or what it does?
Printf.
Yeah, it's printf, exactly, yeah. So basically all it's going to do is going to print the string. So like it's going to print the string that we pass to it. So we'll say then in a high level language it might look something like this. Right? So basically, your nice one-liner of C code just called printf, print my string. Well, that immediately becomes two instructions in assembly because you have to, first of all, you have to pass the string directly to the function and then call the function, okay? But one of the nice things about IDA is, we'll say if you highlight one subroutine like that, it immediately shows you, oh, by the way, this subroutine down here, it's the same, it's got the same name, okay? So you can see straight away, well, like, do you see a pattern kind of emerging there, right? So maybe this was, 3 printfs in a row, all having, we'll say, a different string, okay? So again, like, if you just kind of hover over the offset to the string there, IDA will actually show you what that string is. And if you double click that string, you'll be able to go directly to where it is in the ORData section. So again, just like that. And you can see then that actually we've got quite a few strings here, and they're all part of the welcome message that we originally looked at, right? So again, if you did actually follow that and you're at that section now, just hit escape to go back to where you were, okay? So there we have what looks to be 3 or 4 different strings. They're all being passed to the same function, and we reckon that that function is probably just a print string function, or actually it's actually printf. So like we were saying then, one of the useful things about IDA is it lets you rename certain parts of your code, okay? Because again, reading assembly language is very, very difficult. It takes a lot of time. So you want to basically mark things that you've already seen, okay? So to rename this specific subroutine, then you just hit N, and then you'll be able to call it whatever you like, okay? So in this case, we'll call it printf maybe. So now the assembly language hopefully is beginning to look a little bit more readable. And that's the whole idea behind IDA. IDA doesn't actually do very much for you. Like, you do all the work, IDA just kind of lets you do it, if you know what I mean. So like when you're kind of going through malware or going through any program at all, or maybe you want to have a look at any crackneys that you find on the internet, IDA will let you kind of mark things up, but it won't do any thinking for you. And that's probably maybe the biggest misconception about it, is that people always think, oh, you just use IDA and you'll be fine. You know, you have to put quite a bit of work into it in the first place to get good returns from it, okay? So now we see straight away, okay, this is actually exactly what we thought. It's a function that basically just prints 3 or 4 lines in a row. and then it just returns out. It cleans up its own stack, pops EVP, and then it just returns back to the place it was called from, okay? So now maybe we'd like to see how can we find out where this subroutine itself was actually called from, right? Well, maybe first we should rename it. So we can highlight, we'll say, the name of this function, which is just the unreadable sub underscore 40 AODO, and then just hit N again, and you can say, okay, print welcome. So now, if you're kind of hovering over your print welcome like that, if you press the X key, what it does is it shows you XREFs or cross references. You're basically asking IDA to show me every place in the code where this subroutine is actually called from. So in this case, it's only called from one place. It's called from inside main, which again makes sense because we reckoned, okay, it's the main function, and then the first thing it does is it calls print welcome, okay? So if you click OK or just hit return, now we're back to our main function, and we've started our markup basically. We're basically saying, okay, well this very first subroutine, what it does is it prints the welcome message, and that's really all it does, okay? So, you know, it's not much. It took us a little bit of time to get there, but you know, we're beginning to mark up this, you know, unreadable assembly to something which is a lot more readable. Okay. So now, the next instruction we see directly after this then is one of Alan's friends, LEA, low effective address, and it's moving that address into EAX, and then again, EAX is being pushed right before a call to this time a different subroutine. So what's EAX then in relation to the subroutine that's called directly after it? It's another argument, right? In this case, it's, you know, maybe we're not 100% sure what it is yet. We haven't been able to mark it up. We haven't been able to call it anything particularly useful yet. It just has, we'll say, the default name that IDA gave it in the first place, which is just var10. So again, just like subroutines, anything like that, you can basically just highlight. It will show you every other place it's used, and then if you hit N, you can basically just rename it. So we'll call this arg1 for the time being. So one of the most important things, especially if you're going through very big assemblies, is to make sure that you always mark things up. Even if you don't know what it is yet, just give it a name, because if you see your own kind of handiwork, it's a lot more clear what's going on than if you're just looking what IDA did in the first place, okay? So even though we don't know what this argument actually is for yet, okay, we'll just kind of mark it up just so that we know, okay, we've at least seen this before. We saw that this was pushed into a function. But even then, IDA is quite clever about the type of the arguments and maybe how they're used for inside the next subroutine. So it immediately gives you a hint. It says, okay, this is actually a character pointer based on some information that it was able to put together itself from maybe how it's used in the next subroutine or maybe how it's used further down in the assembly. Okay, so that's an example of a comment that IDA just adds by itself, again, just to try and help you out to see, to let you know exactly what's going on. So then we'll say if you all click into the next subroutine, 40AO, you'll see then that our arg0 is already there waiting for us. We kind of expected that to be there based on the code we saw just outside of this subroutine. We see we have another offset to a string, and this time the string says, please enter the password, okay? And then if you just look even a little bit further down, you'll see that you have a call to a subroutine that's already named. So does everyone know what fgets would actually do? Well, the clue is in, we'll say, the string, right? That's right above it, where we say, please enter the password. So maybe, what do you think fgets is for? It's probably going to get something, right?
Where's the fgets? Sorry.
Fgets? See here?
Does it read in what you typed in?
Yes. So basically what fgets will do is it will read a string from a file handler. In this case, we're going to say it's going to read from standard in. Okay? So yeah, so we basically saw that there was another call to this printf maybe. We saw that the string was actually please enter the password, and then we see a little bit further down we see, oh okay, it's actually called to fgets. Now if it was a case where you didn't actually know what the hell that function actually was or was for, you know, you could go onto the MSDN network and you can basically just look up pretty much any function in their standard library and read up okay, what is it, how does it work, what does it return, what arguments does it take, things like that. And that's another kind of very useful tool, because you have to kind of be able to work out. So okay, we can probably give it a name like, you know, input password. And again, we rename things by just kind of hitting N and then typing whatever we want the password to actually be called. Okay, so now do you think it looks a bit more readable than when we first started?
Yeah.
Okay, yeah, we see print welcome, we see read password. We know that this input password contains what's been input by the user in the first place. So now we can actually begin to track, okay, well, we need to find out exactly how this password is validated, but because we're able to track this password across the entire life cycle of the program, you know, we can see every single place where it might be used and every single thing that might be compared against in the first place, right? So again, hitting X, you'll kind of see all of these cross-references to, okay, your input password is used here, it's used here, it's used here, and then you'll be able to jump directly to those specific locations in the code, right? So now that we've printed our welcome, we've read our password, we know where our password is actually living in the program itself, and then we immediately pass it to the next subroutine, okay? So okay, here we go, straight away, we see we have more kind of string offsets, and this one, again, it kind of shows you straight away, okay, well this is what that string actually is, okay? So the string is actually easy, all right? So considering what we know about the password already, what do you think this is? It's the password, right? So this is probably going to be the validation function where we check against what was input by the user against the actual password itself. Now in this case, we'll say the person who wrote this program, he was really sloppy. He basically just left the password in the binary so that you would be able to find it with something like strings or by Hugh's extract strings function or anything like that. But even if, we'll say, you didn't get lucky, you didn't see it straight away, if you do, you know, if you put in a little bit of time of reverse engineering, you'll be able to kind of see straight away, oh, okay, maybe easy is actually the password, maybe I should just try that. So we still have our first argument, only argument that was passed into this function, which again, hopefully we remember, was the input password that the user itself actually passed into the program directly. And then we see that this is being moved into EAX, and then this EAX is being pushed to this stringlen function, which you can probably guess what it gives you back when you call strlen. It gives you the length of the string, okay? So that's fairly reasonable. So what's he doing? He's basically saying, okay, let me first check what the length of this string actually is. I read it in from the user, now I'll just pass it directly to stringlen. Okay? And then because all return values from, well, most return values from subroutines, they tend to put their final return values into EAX before they return, if you know what I mean. So in this case then, he's basically storing that length into this variable. Okay? So you see the way that you can kind of gradually build up a picture of what's going on in your assembly language, okay? So the next thing he does then is he's going to pass this var8 again to stringlen. So can anyone guess pretty much what this check is actually doing?
Checking whether the string length matches there.
Yes, exactly, right? So it's checking that the length of the string that was passed in matches the length of the password that is written into the program directly, okay? Okay, and you can kind of see the way then that the compilers, the way they work is they're kind of very stupid and very smart at the same time. They write assembly language the way no normal human being would ever write assembly language, but they're also very set on patterns, if you see what I mean. So that you're always going to see these type of patterns kind of repeating themselves over and over. So like, you can see that this is pretty much the exact same code, right? More or less. That basically it's setting up the register that it's going to pass the string into the subroutine with, and then it's going to call the subroutine, and then it's going to do something with EAX. You know, that sort of way. It's basically just the way the compiler produces this type of code, okay? So now we have basically two lengths. We have the length of the original password, and we have the length of the input string, okay? So here we have our actual comparison. So EAX, again, that's the return value from the string strlen function itself. We move that into a variable in the program called original length, okay? We then take the variable, the input length, and we move that into EDX. And then we just compare EDX against the original length, right? And then if it's 0, we're going to do a jump. So this is an example of one of our conditional jumps, right? So what does compare do? Does anyone remember that from their assembly?
Subtracts one against the other and doesn't store the result.
Yes, very good. So it doesn't store the result, but what does it store? Or what does it?
Sets the flags.
Yes, exactly. Very good. So we'll say this is the case then, we just check, has the 0 flag been set? Okay? So basically that's basically saying, are these two numbers the exact same? Subtract, we'll say 3 from 3, you're going to get 0, right? So we'll say if the 0 flag is set, then we're actually going to take this short jump and we're going to continue, okay? If it isn't set, then we're going to XOR AL with AL. So I don't know if you're familiar with the XOR instructions, how they work. Basically, it'll 0 out AL, and then it's going to take an unconditional jump, all right? And if you follow that unconditional jump just by hitting return on the location that it points to, you'll see that you come immediately to a function epilogue, where basically undoes what was done at the very start of the program, and then it returns, okay? And then IDA is kind of clever enough so that it will basically tell you, okay, well, this is the end of that subroutine. It gives you an NP, and then it's the name of the subroutine, right? So now we see straight away, we can already say, give a good idea about what this code is actually doing. Very first thing it's going to do is it's going to check the length of the input string versus the length of the password string that was written into the code. If they don't match, it's going to immediately exit, okay? So that sounds like reasonable. I say it sounds like reasonable code, even though I wrote it myself. But like that's a reasonable way to do a password check, right? The very first thing I would do is, okay, do the password lengths match? If they don't, I'm just going to quit. I'm not going to do anything else because why waste cycles when you don't need to, right? So that's probably your very first check. So am I going too fast, guys? Is everyone following? Like, does it kind of make sense even how we're kind of going through the program to work out what's happening? I don't know if I'm seeing a lot of blank faces. People playing with phones. So I know it's a lot to kind of throw at you, but like it's a case where we can go through it as much as you like, really, and we can just try and make sure that you get something out of how reverse engineering actually works, what's involved with it. And it's probably worth mentioning that this is all an example of what's called white boxing an application. Okay, so we'll say in reverse engineering or kind of maybe malware or binary analysis, you have kind of white boxing and black boxing. So we'll say black boxing is where you might take a specific binary sample, you would just put it into a virtual machine, you would execute it, allow it to run, and then look at what were the side effects that were created on the virtual machine or the system itself once the binary had finished executing. So you basically treat it as a black box. You don't care what's inside it, you just care what it does, what is the final change of state, I suppose, to the operating system when it's finished executing. So white boxing, which is what we're doing now, where you actually kind of look directly inside the binaries themselves, is much, much harder. It takes a lot of time to kind of go through these type of things. But you will learn exactly what's going on because there are loads of different tricks that you can do to kind of, we'll say, detect whether or not a binary is actually running inside the virtual machine, detect if it's been attached to by a debugger, and these type of things. So if you really, really want to know exactly what's going on in a binary, this type of white boxing, even though it's kind of slow and kind of tedious, is really the only way that you can be 100% sure. Okay. So now that we know that this is actually a success, we'll say that this jump basically means that, okay, our first check is passed, we can hit N and then we can rename it. So now that we know that just after this, at this XOR AL, we have this unconditional jump, which means that once, let's say, we get to this point, we're going to jump no matter what. We just go, basically. We know that this is actually the end of the program, so we can just call it exit, or sorry, not the end of the program, the end of the procedure. So we call it exit or end, whatever. Okay? So now again, you see the way it just becomes a little bit more readable. Now you're kind of saying, okay, well, there's a compare here. If the 0 flag is set, well, then we jump to the label first check passed. If the compare isn't exactly the same, well, then we're just going to call XOR AL, and then we're going to jump to the exit of the procedure, okay? So again, do you see how you kind of can get a much clearer view of what's going on just by, like, we didn't do anything particularly special. All we did was we read assembly language and then we renamed things. We haven't even used a debugger to see what's actually happening, right? This is kind of, you're going in cold, more or less. But this is just kind of one of the things why IDA happens to be so popular. So now we're down to first check passed. And I can tell you straight away that this is basically just a validation loop where we're going to go through the 2 passwords and we're going to basically check, does this character match this character at this specific part of the string? And again, if any of you have done kind of basic programming, you might think about how you've compared the contents of 2 arrays to each other. It's basically the exact same thing. Okay, just unfortunately broken down into assembly. Unfortunately. Okay, so straight away we see that we're moving this 0 into a variable. Okay, and again, this is one of the variables which is declared inside the actual procedure itself. Okay, so straight away, anyone who's done this type of loop programming, any idea what that might be used for? It's a variable that you declared inside the procedure and you've initialized it to 0.
Your test variable for loop.
Yeah, that sounds reasonable to me. Yep. So again, if you hit end, you might say count question mark. So again, you're just kind of trying to make things as simple as possible for yourself. You're kind of saying, okay, well, this looks like it might be a counter. I'll just label it so that it doesn't confuse me later on. And then if you highlight it, if you basically just click on that specific variable, you can see that it's used all over the place, right? So now you can see, okay, well, we're initializing it here, and then it looks like, oh, we're actually incrementing it here, right, by adding EAX to 1, and then we're moving that value back. So that looks like an increment to me. So this is beginning to look how a for loop might look in assembly language, right? And then if you kind of follow this code down, again, we were kind of saying this is probably an increment. You can see then that we also have a check. So this count variable that we saved, we move it into ECX, and then we compare ECX versus this original length that we named beforehand, right? So again, this kind of gives you an idea that the work that you do earlier on can kind of come back to help you later on. Because if we had just left original length as var_1, 2, 3, 4, we wouldn't know what the hell it was. We'd have to keep kind of going back to check what the hell, you know, what it was actually used for. And that's, we'll say, the main benefit of these type of IDA programs, is that you can kind of mark things up as you go along, right? So now we have a good idea that, okay, this code here, you know, it's moving our count variable into EAX, it's adding 1 to EAX, and then it's moving it back into the count variable, right? So it's moving it from memory to register, incrementing the register, and moving it back to memory. So if you hit end, we can say increment count.
I'm going to check if everyone's still on the same page.
So is everyone following along? Does anyone have any kind of questions? Okay, so we can kind of keep going through the assembly language and we can kind of talk about it, or you can kind of work along by yourselves. Yeah.
I don't have the preference to look along and think probably go faster.
Sure, yeah. Okay, so if you want to maybe even continue on with this one, and, you know, if you have any kind of issues or questions, just give us a shout and we'll kind of come up and have a look at them as well.